Good morning and welcome to our calculus session. Let me just finish my setup here. Okay. Technically, we're still in chapter 9, but I kind of like to put this in our next, not chapter, topic. Topic 10, I'll call it optimization because that's what it's called. Now, for the next two topics, what's going to happen is we have a little bit of an intro, and then the main portion is talking about the word problems and the quote unquote applications, even though they're still very simplified to make it manageable for us. It is technically an application. So we want to get a little bit more practical here, but there's a little bit of a warm up before we can do that. Let's just look at a function. Let's just take a random function, and its graph. And let's just see things that we've seen before, but let's just make one up. I could have something like this. I see a critical point here, critical point there, and out of my increasing, decreasing behavior, I would find these critical points. Now, usually the functions that we look at are defined for all values of x, or most values of x, and they keep going forever, far to the left and far to the right. But when it comes to practical problems, often I have a restriction on the x values. Perhaps my x values are cut off, and for practical reasons, I'm only looking at this window a to b. Even though, mathematically speaking, the function does continue forever, it doesn't make sense practically to look at all the x values. So there are mathematical restrictions, like dividing by 0, or the log function not being defined on the left side, stuff like that. Then there will be practical restrictions as well, usually giving me some window that I have to work with. Once we have that, we're limited to a window, whether that window might be given to me in terms of an interval, or I have to think about the practical situation. Regardless, because I have that, I often have these endpoint situations that past this endpoint, I can't look at anything further. Now, for a critical point, usually, if it changes from increasing, critical point, horizontal slope maybe, or a vertical tangent, whatever, to decreasing, I have this turning point, and I'll call it a local. In this case, it's a maximum. This critical point over here, it's a different kind of turning point. We'll call it a local minimum. Local because when I zoom out, or local, let me rephrase this. Local because when I zoom in, zoom, that's aggressive zooming, but when I zoom in and I look at a very small window, at that critical point, it is the smallest y value I'm going to get for the immediate small area that I'm looking at. But of course, as I zoom out, overall, it might not be the smallest y value I could get. Or it might be. Those two aren't necessarily the same. Same for this local maximum. While I erase these little lines, if I look at a very small window around this turning point, that is the largest y value I can get. However, when I zoom out, there are larger y values over here, right? These are bigger. So we call it local or relative because it's only applicable to the immediate surroundings. I'm very zoomed in. then it is a maximum or a minimum, an extreme point. But when I zoom out and look at the whole interval, whether it continues forever or I cut it off, it might not be the best anymore. So over here, I see I have the point that gives me the largest y value across everything. We'll call that a global maximum. And in this case, it's an endpoint. In some cases, like for the minimum here, this local minimum across all the valid points is also a global minimum. So sometimes the critical points are local only, sometimes they're global. Why is there such a huge space between my G and my L? That looks really strange. Sometimes the critical point is only local, and there is an endpoint that gives me a more extreme maximum or minimum y value. So the endpoints can also be extreme values. However, when I look at the function, just mathematically, it doesn't know my window that I'm interested in. It goes forever. And it's not going to point out this point as anything of significance. So it will, however, give me the critical points. It won't give me the endpoints because it doesn't have endpoints from its point of view. I have this extra restriction, or I'm given an extra restriction. So I have to manually check if the endpoints give me better results or not. That's really the only issue. I have these turning points, local maximum, minimum, but the endpoints could also be more extreme or better points. Like this endpoint over here on the left, it's nothing. It's not the highest, it's not the lowest, it's nothing. But if I don't check them manually, I might not know. So let's look at a problem. And let's look at problem. It's actually still in topic 9. I'm going to look at 9.8, not the whole thing. So, sorry, global, I should say that, I did not. There are two ways of naming these. Local can also be called relative. Global can also be called absolute. Just multiple names for the same thing if it's not confusing enough. So I'm going to look at finding for a function. They give me the interval. Let's just look at maybe C. Why not? Find the absolute maximum minimum values on the given interval. So whether the interval is given to me or it comes out of a practical problem, I have to then work with that interval. And though the function x squared minus x minus 6 doesn't care about any restriction on x, there's nothing. I now have a restriction, and it's the interval 1, 2, 3. Now I can visualize this if I want to, but I don't really care to put any effort into where this graph is sitting, right? But for the sake of visualizing something, we can have a quick idea here. I have a y-intercept of 6. Oh, I made this way too low, didn't I? Let's put an x-axis in a more neutral position. For y-intercept, I have negative 6. Axis of symmetry, negative b over 2a. That's going to give me a positive value. Okay, so it's going to sit somewhere over here, it looks like. I don't really care. Right? It doesn't matter at all. I have 1, 2, 3, and I don't know where these guys sit. What I have to check first, I have to check for critical points. And the reason I don't really care what this looks like is I'm going to very soon have functions I don't even want to graph. They're going to be too messy, and I can't rely on my graph to read off any information. Check for critical points. How do I do that? Well, that's technically step 3. It's not the full step 3, but it is the essence of step 3. So let's do step 3. For that, I have to find the derivative, which is easy because it's a simple function, 2x minus 1. How do I find critical points? I check where is the derivative equal to 0, where is the derivative undefined. Well, it's equal to 0 when x is 1/2. And it's undefined, never. So my critical points are only when x is equal to 1/2. I have a y value that I can find. I'm going to leave it out for now on purpose. But do note, of course, for a critical point, I need to have a point there, which I do because it's a polynomial, so everything's good. And it's the only one coming out of this check. So it's not the full step 3. I don't care about a table. I don't care about anything like that. For pluses and minuses and increasing and decreasing behavior, nothing like that. Because it's actually much simpler. It turns out that the only place I could have these extreme points is when the graph is turning. It could be a sharp turn, but it has to be a turn. And that's only going to be critical points. These will always be critical points. Critical points. Or endpoints. It doesn't matter how it behaves. If it's not a critical point or an endpoint, it cannot be a maximum or a minimum of any kind. Only the endpoints have to be checked manually. So I am going to make a little table. I guess technically it is a table, but it's not the same kind of table that we did in step 3. All I have to list now, make a small, easy table just to see. What do I have to check? I have to check the critical point. I'll emphasize that here. That's my critical point, and I only have one. Otherwise, I would have to list them all. And I have to check the endpoints. And the endpoints are given 1 and 3. So now I have to plug it into my function. My function was x squared minus x minus 6. I have to plug in these guys and see what the corresponding y value is. So I'm gonna do the first one, and you can do the other two, and that way we save some time. 0.5 squared minus 0.5 minus 6. For the first one, I get negative 6.25. Now you can tell me what is the y value when I plug in a 1? Oh, that's super easy, isn't it? 1 minus 1 is negative 6. Sorry, I didn't mean to do that for you. You can do the 3. Plug in a 3 into your calculator and tell me what do you get for the y value. I don't think my graph is very accurate. Oh, 0? Oh, all right. Yeah, I don't think my graph is very good at all. Can't rely on that thing. And soon I won't have a graph anyway, so whatever. It doesn't even matter. So the key thing is that any maximum or minimum can only come out of this list. So all I have to do is pick the point that gives me the highest y value pick the point that gives me the lowest y value. So my absolute or global minimum is y equal to negative 6.25, and that is happening at x equal to 1/2. My absolute or global, pick whichever name you like. Global maximum is 0. It's the largest of all of these values. And that happens when x is 3. So just for the sake of argument here, I think my graph is way off. So let's suppose I have 3 and 1, maybe like this. You see that this critical point that we got, this is, I don't know, this isn't very good. Oh, no, it's backwards. I see, sorry. It's backwards. Let me fix this. I went too fast. Let's put 1 over there. And 3. There we go. There we go, there we go, there we go. Okay. So what do I see here? I went too fast. Let me just move that out of the way. So forget I wrote the last sentences. My interval or my window is 1 to 3. So I got a critical point, forget the scale here, at 1/2, but my window is 1 to 3. Once I have an interval specified, they specified it, or for whatever reason, I am stuck to that, and technically nothing else matters. When I look at the whole graph, for this parabola, there is a minimum at 1/2, right? It's the lowest point. I get to negative 6.25. But on the interval, that's not allowed because x can't be 1/2 on this interval. I have to, unfortunately, say that doesn't apply. So let me summarize this in a better way. So it's going to be better here. Overall, get rid of eraser mode. Overall, my global, my absolute minimum is negative 6.25. If you forget the interval, you look at this parabola, it has a minimum point at x equal to 1/2. And my global maximum does not exist, right? The parabola keeps going up forever. So I want to draw this distinction. I was a little bit too fast with my writing here. It's just none. There is no maximum because it goes on forever. See, the arrows go on forever. However, in addition to the parabola, in addition to the function, if then an interval is specified, nothing else matters. Outside of that interval, literally it doesn't exist. It doesn't exist. Only that interval exists. Then my global minimum, this doesn't exist anymore because it doesn't fall in the interval. My global minimum is this lowest point on that interval, which is negative 6, and that happens when x is 1. And my global maximum is the largest y value I get out of the table of valid points, which is 0, and that is when x is 3. So it's a very good example. I just wrote a little too fast. On the interval, I get different results than overall. If I just look at the parabola, the function says, this is my property. I have a minimum, I have a turning point at the bottom. Maybe you want that. Maybe you don't. I don't know. I have to manually match that information with a specific interval to see the critical points that you have, are they of interest to this interval? Do they fall inside the interval? Maybe, maybe not. If not, nothing outside of this interval matters. It doesn't matter. But the function didn't know that when I find the critical points. I have to manually just list all the points that are interesting, including the endpoints of the interval, keep what's inside the interval, and pick the best, highest, lowest of those. All right. So let's maybe do one more. Technically today is just reserved for this, but it's not a huge topic, and I think one more example will be sufficient. Because maybe my hasty writing confused people. So here's my function, 1 over x plus x. I'm not going to draw it. I don't know what it looks like. I also don't care. And the interval is -4 to -1/2. Okay. So now I want to find, are there critical points, and do any of the critical points fall in that interval? Let's hope there is something this time. So of course I'm going to write this as x to the -1 plus x, so that my derivative is just consists of basic properties. -x to the -2 plus 1. Now in order for me to see clearly what the potential critical points are, I need to maybe clean this up a little bit. So I'm going to write, let's do it all in one line, -1 over x squared plus 1. And then put everything over x squared, and I get -1 plus x squared, simplifying back to that. Maybe I want to make it look as nice as I possibly could. I'll do it over here. That's x squared minus 1 over x squared. And that is going to be the difference of two squares. So I can factor that, just making my life as easy as possible for the next bit. Then I can say, oh, this derivative is 0, clearly when x is 1 or -1. And the derivative is undefined when x is 0. Okay. Now at 0, I have a vertical asymptote, right? So this is not a critical point. Y is undefined here as well, because I can't divide by 0 up here. So it's not a critical point. And luckily it doesn't even fall in my interval. But this guy does, right? This guy is in my interval, in the interval. So there are properties of this function, vertical asymptotes, and all kinds of other stuff perhaps. But when I look at my interval, I don't care about those things. It's not inside my interval. It doesn't exist to me. I don't care. But when I do this derivative, it doesn't know what the interval is. So my little table will have the x values that are of interest to me. I have an endpoint, I have a critical point, and I have the other endpoint. The critical point of 1 is a critical point. It's not in my interval. I don't care. It doesn't matter to me then. So now my function was 1 over x plus x, right? So I want to find the y values corresponding to these guys. So that was a critical point. That was an endpoint. Not that it matters. That was an endpoint as well. So we plug some in. We find some y values. Let's see what we get here. I'll do the -1/2 one. So that's a -2 plus another -1/2. That's -2.5. So that's negative. Let's do decimal maybe. It doesn't really matter. No, it's a fraction. -1. Work on the -4 while I'm doing this. -1 is still -1, that first term, plus another -1, so that's -2. And then -4. I did 2 of them. You should do 1. plug it into your calculator or leave it as a fraction. Doesn't really matter to me. You can go decimal here. You could say negative 2.5. Doesn't matter to me. Negative 4.25. So now, out of this list, I want to find, in this case, both the maximum and the minimum. Whether you call it absolute maximum, global maximum, minimum, whatever. So my largest y value, well, they're all negative, unfortunately. Largest one is going to be this negative 2, right? And that's going to happen, in this case, at a critical point. The smallest one of these will be negative 4.25, and that happens to occur at the left endpoint. I don't know what this graph looks like. We could totally graph it and figure it out, but that's not the point here. And when I cross over to the practical problems, the functions are not going to be pleasant to graph. They're not going to be super difficult, but it's a whole other issue to go through all those graphing steps. That's not the point. So I have to be okay with not knowing what the graph looks like, not being able to visualize it, just trusting that I can only have an extreme point like this at a critical point or at an endpoint. Nothing else could possibly give me the best value. Best meaning maximum or minimum, depending on the situation. So I have to, as nice as it could be to visualize this, it's wasted effort to only find the largest and the smallest y values. Okay. So now we'll cross over. Let me know if there are any questions as I set up the next little bit. There's good news and bad news. The bad news perhaps is things sometimes when you look at practical problems, things can get a little more messy and you have this word problem layer on top. The good news is there's no new mathematical concepts to worry about. I just have to practice some examples. So we're looking at number 10, optimization. I didn't mean to maximize that. We'll start with something easy. We have the next 2 sessions as well. I'm pretty sure. So let's make the first one nice and easy. Cannonball movement. A cannonball is shot vertically upwards from the ground with initial velocity 15 meters per second. The height of the ball, y, they define the variable for me, that's always nice, as a function of time t is given by that function. Now, this should have just put the 15 in, or whatever. I want to determine the following things. Determine the time at which the cannonball reaches its highest point. And then some other stuff. All right, so let me just copy some stuff over here. We have a problem 10.2. We're looking at number, oh no, that is the number, I see. Okay. Good, 10.2. So I have my function, y equals 15t minus 4.9t squared. Now remember, this is a word problem. So it always starts with define your variables, then set up the function, then solve whatever you need to solve, and write a concluding sentence. However, a lot of this is done for me in the first question. Later on, it won't be. They've defined the variable for me. So if I look at this, because it's a fairly simple parabola, it's going to go up and it's going to fall down again. The height over time is going to increase as the cannonball is shot up, and then it's going to come back down because of gravity. Okay, so it's not a bad first example, yet practical. All right, so there's my function describing this up and down movement over time. I want to know when it reaches this highest point. Well, first I want to know what is the highest point. So I want to find the maximum y value. Now again, if I look at this function, it's not the one I drew. That function, the function here mathematically goes on forever. It's a parabola. Yet I put in a restriction. I don't exactly know what this end time is, but I'm not interested in the cannonball going through the ground below the ground level. It doesn't practically make sense. So I immediately add a practical restriction in by way of an interval. So my interval is going to be 0 to some end value. And I don't necessarily know what that is, but visually I do. It's restricted to this window. But because of the kind of function, so here and here, my y value is going to be 0, and I'm looking for the maximum. So it's not going to be at the endpoints in this case, though I could consider and include it. It's going to be at this top critical point. So I need to find the derivative, which isn't terribly difficult, and then ask, where is this derivative equal to 0? I don't have to ask the undefined portion because it's a polynomial, and that'll never give me anything. So it's going to be 0 when I set this equal to 0. And that means that t is 15 over 9.8. Let's see if that gives me a nice number. I'm not interested in rounding this early. 15 divided by 9.8. No, of course not. It's going to be unpleasant. But it's good. It's good, good example. 1.5306. When I present decimal numbers, I might write them down and round them. I like 4 decimal places, so I have some decimals to work with, but it's an arbitrary choice. 4 just makes me feel better. This is not the number I should use in future calculations, if there are any. I should always use the accurate version, though when I write it down, I might round it. If I use the rounded number in future calculations, I could lose accuracy, and my answer might not be correct, and that might matter. So just be aware of the distinction between presentation and calculation. I don't know if I'm going to need this in the future, but I want to be ready and aware of that. So I can make my little table if you want, just for the sake of it. My t values and my corresponding y value. I have my endpoint 0, and I'm not exactly sure when it falls yet, but there is another endpoint, and I think we're calculating it later. And then I have this 1.5306. Now I know at the endpoints my y value, my height is 0. I want to find the y value at this, and again, there's a calculation, so I'm going to use this accurate t value, not the rounded one, when I plug it into my function. And my function is up there. So let's do that. And I encourage you to do that as well. I can't speak and type sometimes, so I apologize if it's quiet in the live session. So we have 15 times 15 divided by 9.8 minus 4.9 times brackets. I need brackets. 15 divided by 9.8, and then I square that time. And you can actually go and see, if I use the rounded version, how does it compare with that answer? You'll see it is not the same. And you might say, oh, but those decimals don't matter. Well, how do I know practically speaking, which decimals matter and not. I want to be as accurate as I can. So if I round this, I'm just going to write the full one, though you could see it in the chat. If I round it to 4 decimal places, which is a good rule, it's going to be a 6 here, right? Undo, undo, undo. 6. Knowing that if, I don't think that's going to happen, but if there is a future calculation with this value, I need to use the accurate one, which I can see. If you type all the decimals, that's accurate enough. All right, so I'm looking for the largest one, so clearly it's this one. So the maximum height is 11.4796 meters, and that is happening at time 1.5306 seconds. Okay, so there's my answer for the first bit. We'll just do this one. These questions, they can get lengthy, especially as we take our time and talk through them. All right, then they tell me, so I have the time at which the cannonball reaches its highest point. It's at 1.53 seconds. I want to know the velocity and the acceleration of the cannonball at time 5 seconds and 1.5 seconds. I'm not going to do all of that because if you can do it for one, you can plug in more values. That's a little silly. But let's do it at least. Velocity is the derivative. And we already found the derivative as 15 minus 9.8 t. So the velocity at, let's just do the first one, 0.5 seconds. I can find that. Acceleration is the derivative of the derivative. It's the rate of change of the velocity. So it's going to be the, whoops. It's going to be the second derivative. And that's going to be negative 9.8, which is the gravitational constant rounded. So it's constant. It doesn't even change. So I'll just emphasize here. It's constant. Oops, that was an N and an A. Oh, my writing is so sloppy. I am just buying time so you can calculate the velocity at 0.5 seconds. No one? All right, maybe we'll come back to that. And you can then plug in 1.5 as well, right? It's quite straightforward to do. Calculator stuff. You can teach a monkey to use a calculator, but they have no understanding of what they're doing. So I'll put some dots there, and maybe someone wants to tell me in the chat what it is. Maybe in the YouTube chat, I haven't checked. No. 10.1, perfect. Now, is it perfectly 10.1? Oh yeah, I guess it is. We just want to round consistently. This doesn't look like a long decimal number. 10.1, perfect. That'll be meters per second. This will be meters per second squared if you're interested in the units, and we're not that interested. All right. Let's get to something more interesting. This is just sort of plug and play B question. The time at which the cannonball hits the ground. So we said earlier that I don't know exactly what that time is, but I know there is such a time. But I also know that it's when the height of the cannonball is 0 again. So by setting y equal to 0, I'll find the end time as well. So let's do that in our last 5 minutes. So this is now C. Set y equal to 0 and solve. What is my function? 15t minus 4.9t squared equals 0. Now, this isn't the full quadratic equation, so I don't have to use the quadratic formula, though I could if you wanted to. It's unnecessary though. By factoring out a t, I'll save some time. So t is equal to 0, or 15 minus 4.9t is equal to 0. And this one tells me t is 15 divided by 4.9. I don't know what that is. Let's see. I know it's going to be double the height time because I have some nice symmetry here, that the center of the parabola is exactly halfway between the two t intercepts here. But in general, I might not have that symmetry. I didn't even care to actually rely on the graph. So it's a nice extra verification, 3.0612 if I round it. So a little concluding sentence here is nice. The cannonball is what we're working with. Cannonball hits the ground at about 3.0612 seconds. And the first value that came out of this was, of course, the launch time. So some nice things you could do. This is a little physicsy question, I suppose. And not everyone likes the physics side of things. We'll try and mix it up to maybe give everyone a kind of question that they like. But this is still, yes, it is more practical. It is an application. But we are trying to keep things incredibly simple still, just to illustrate the point of how derivatives are used to find maximum or minimum values in a changing quantity that's described by some function. Right, are there any questions on this? As I see our schedule again, I'll bring it up. Little things keep changing in the schedule, so do check regularly that you are looking at the most up-to-date schedule. I've said these things yesterday as well. We are over here, March the 11th, getting close to the end. And yes, tomorrow is a yellow block. I did put, it's a series of smaller videos. I already put them in our playlist. All I did was just work from start to finish. Well, not me, the cat did it. From start to finish through all our types of functions, our 5 types, all the graphing steps for each type. So that just you can see, you can look at specific ones you want to look at. You could watch them all if you want. Use it however you want, just extra stuff. And I wanted to attach that to a weekend because it's longer than just a single session. There's no that because I don't want it to be extra work for you. So I give you a session time, but it's not a live session. You have tomorrow and the whole weekend to do it if you want to. So no additional lesson. That is the videos you can work through as you need, or then we'll continue this topic 10 on Monday with a couple of days of more word problems just to see the variety that we want to be ready for a midterm. There's some variety in these questions, some common themes as well, but we want to have a couple of days of practice there, followed by another Q&A session just to help people catch up if they need to. Also note, again, I'm just repeating myself to make sure people see the updated schedule. Friday the 19th and the following Monday are yellow video blocks as well. I had to change those. Those are not videos in the playlist yet, but they will be by the time that we get there. And as always, let me know if you have any questions. I'll still be uh, there within email contact reach, of course. All right. So I won't see you tomorrow. Enjoy the weekend. Try and catch up if you haven't. Lots of things to practice. It's really just practice over and over and over. If you need me to check anything in the problem book, send me an email. Some people do. I'm happy to do that. Otherwise, have a good weekend.